Kia ora koutou, no mai, haere mai. Welcome to lesson 6 for introductory physics on projectile motion. With projectile motion, we're not really learning any new physics. We're going to take what we already know about simple motion with constant acceleration, and we're going to apply it to projectiles, which are things which are only being acted on by gravity due to Earth. So they've got the constant rate of acceleration due to gravity. Other than that, it's just going to look a lot like what we've already been talking about. But it's worth spending this extra time discussing these problems because they're such a common set of problems. These projectiles are literally everything in the real world when you observe it being thrown or falling or anything like that. So as usual, there's a few learning outcomes. Decomposing motion into horizontal and vertical. We've already talked about decomposing. We've already talked about frames of reference. So this is just saying, take your frame of reference and decompose vectors into that frame of reference. So nothing new there. Then we're going to talk about graphs for projectile motion. We're going to talk about the kinematic equations that we've already met, but for projectile motion. And we're going to talk about a few assumptions that we make. And then we're going to, finally, we're just going to slightly, not off topic, but just slightly push projectile motion to its limits and talk about orbits such as the International Space Station. So when we've got something moving in 2 dimensions, we need to decompose its motion into each separate dimension. And this comes back to that frame of reference discussion that we've been having consistently throughout this course. Hopefully you're all not getting sick of me talking about frames of reference, but are already thinking about it at the start of each lecture, just remembering that that's something we need to be thinking about constantly when we're doing physics, because it's very important. So often we'll use X and Y. And whenever we've got 2-dimensional motion, as we talked about with graphs, we graph them separately, we treat them separately in a lot of ways, in fact. And so the best way to deal with projectile motion is exactly the same. We just break everything down into vertical and horizontal. So if something starts with some velocity v at an angle theta relative to the horizontal, again, we already know how to decompose this. We saw decomposition in lesson 3. That just means break it down into its 2 component vectors, each one parallel to one of the 2 dimensions that we've chosen, the 2 axes, x and y in this case. So we have Vx is equal to V cosine theta and Vy is equal to V sine theta. Again, we've got little subscripts, x's and y's in here to represent the velocity just in 1 dimension. So rather than writing V equals V cosine theta times our coordinate x, we just put the little x in the subscript, and that reminds us that we're just dealing with that coordinate, that dimension. We can decompose acceleration the same way. When we work with forces, we'll have to start doing that. We'll have to start looking at decomposing acceleration and thinking about the effect in each dimension. But for now, for projectile motion, we are only working with acceleration due to gravity. And because acceleration due to gravity is only vertical, in fact, that's how we define vertical. Vertical simply means the direction in which things fall. We don't need to decompose it. We don't need to worry because we already know that acceleration is only ever going to be in the vertical direction. And for projectile motion, we are always going to choose coordinate systems that have vertical and horizontal as our frames of reference. I know I said that you're allowed to choose any frame of reference you want, and to be fair, you are. If you really want to do that, you can choose a different frame of reference for your projectile and then decompose acceleration and make things really complicated for yourself. But I'm going to always assume that you'll take the simplest approach and choose a frame of reference in which we have vertical and horizontal as our 2 axes, and therefore acceleration due to gravity is only vertical. Remember though that the acceleration due to gravity can be plus or minus depending on the frame of reference you choose. So if you choose down to be positive, then acceleration due to gravity is going to be positive 9.8 meters per second in the y direction, and vice versa if you choose up to be positive. You also recall the kinematic equations. Excuse me. The one that we saw and used a couple of times is that change in displacement, which is equal to VIT plus a half AT squared. And then also the velocity changes for constant acceleration. Change in velocity is equal to acceleration times time. Remember that these are only applicable when we have constant acceleration, but of course gravity on Earth is fairly constant. What we're going to do though is just have a quick look at how gravity does vary. Because again, whenever we make models, we use mathematical models, then we're making a bunch of implicit assumptions. But I'm not going to leave them implicit. I'm going to say the assumption. The assumption here is that gravity is always constant everywhere around the Earth. And we're going to have a quick look at whether or not that's true. Does that hold? So at Earth's surface, this is a theoretical model for gravity again. So again, this model for gravity is making some assumptions, but it's pretty close to true. So at Earth's surface, we have gravity of around about, I should say acceleration due to gravity, of around about 9.81365 meters per second. As you go to the top of the tallest building in the world, which is 828 meters, when I wrote this slide, I can't recall if it's updated since then, we have gravity slightly less. You'll see that it's 9.81056. And then at the top of Mount Everest, by the time you get up 9 kilometers, you've dropped all the way to 9.78598. So just below 9.79. So you can see that even going up to the top of Mount Everest, we're not really changing much. 9.81 down to 9.79, right? It's not a huge jump in that acceleration due to gravity. So unless you're doing really precise measurements, we can pretty much stick with 9.81 or 9.80 here in New Zealand. And so it's fine, especially when we're sticking with 2SF, 9.8, that's definitely true. If you're going with 3, 9.81 or 9.80 is going to be all right. By the time you get up to the altitude of the International Space Station, which is around about 300 to 400 kilometers up in the air, up above Earth's surface, it's not in the air anymore, then gravity, the acceleration due to gravity has dropped to 8.61192. So it's dropped significantly, 9.8 down to 8.6. You may think that there is no gravity by the time you get to the International Space Station, but as you'll see at the end of this lecture, that's not what's happening with the ISS. So that's one of the assumptions of our model, is that whenever we're dealing with projectile motion, we can treat the acceleration due to gravity as just a nice constant rate. If we're talking about projectiles for this whole lecture, then we want to understand what projectiles are. So what do we mean by projectile? It is any object which has some kind of horizontal motion while also accelerating towards the ground due to gravity. So therefore, any thrown object is a projectile, as are launched objects. But as a general rule, projectiles do not have any way to change or modify their own motion. So they don't have propellers, they don't have any way to use air resistance or drag to their own benefit. So we can't use planes or gliders or anything like that. But we can use balls and rocks, bullets, arrows, and so on. Arrows, the little feathers on the end of arrows, they're for stabilizing the flight path. They're not to try and raise the arrow up or anything like that. Projectile motion has two separate components. We've already talked about the frames of reference. We're going to use vertical and we're going to use horizontal. And so if we break any motion for a projectile down into those two separate components, the motion in the vertical direction and the motion in the horizontal direction, then we have two essentially independent sets of information that we can use to solve. And occasionally we'll pull data back and forth between them, but we can solve the equations for each dimension while sort of ignoring the other one. In the vertical direction, any projectile is always going to have a constant acceleration of 9.8 meters per second downwards, per second, I should say, downwards. So that's either positive or negative, depending on your frame of reference, but it's always downwards. And the horizontal component, as long as we're assuming no air resistance, then there's no acceleration. There's nothing causing the velocity of a projectile in the horizontal direction to change. We'll talk more about this in the next section when we deal with forces. We'll come back to thinking about projectiles briefly. But essentially, the upshot of all of that is that there's no acceleration in the horizontal component, so we have constant velocity. And that means we can use our simpler equations for constant velocity, where the change in displacement is simply equal to the velocity times the time interval. If we plot those separately, or sketch them, I should say, separately, we have red going horizontally, and you'll see that each little dot there representing whatever object we have is evenly spaced, because the horizontal velocity is not changing. Evenly spaced dots, not changing horizontal velocity. Vertical velocity is increasing downwards because we are accelerating downwards. That means that if this object starts in that top left corner, then every time interval, the vertical velocity will increase, and so it will travel greater distance between every time interval. So you can see that that's what's happening here. It starts with very little velocity, the next one it's got a bit more, then a bit more, and then a bit more, and so on. And if you draw both of them and then you combine them so that one object is experiencing both of these at the same time, so that it is moving horizontally with a constant velocity and vertically with an accelerating velocity, then we get that purple path. that projectile motion. And that shape is called a parabola, and that parabola you can see all around you. If you look in everyday life, just observe the world, everything falls in parabolas. That's just how it works. You watch a ball traveling in a sports game that gets kicked up in the air or thrown up in the air, it will travel in a parabola. If you look at the sparks coming off a firework, as on the left photograph here, they are traveling in parabolas, and water being shot out of a fountain, that is traveling in a parabola. So everywhere that there is projectile motion, anything that is just being affected by gravity, nothing else affecting it, it's going to travel in a parabola. So as I said, all we need to do is break it down into the two separate dimensions, treat each one separately, apply all its own equations. For the vertical direction, we have to use our kinematic equations with constant acceleration. And for the horizontal dimension, we have to use our constant velocity equations, which obviously are a lot simpler. So this is just a repeat of what we've already said. The velocity in the horizontal direction is never changing. I just want to really, hopefully, drill that home. So that means we can use our simpler equations. Velocity is change in displacement over change in time, and change in displacement is velocity times change in time. For the vertical motion, we'll stick with those four kinematic equations, but what you'll notice here is that I've already put in the acceleration due to gravity. Right? I've put in 9.8 for the acceleration due to gravity. The thing you have to be careful with, though, is that I've written it here with positive g, positive 9.8. You obviously need to, actually no, sorry, I've got that as negative. I've mixed it up. That's not very good of me. What you need to do is make sure you are keeping track of whether acceleration is positive or negative. So we're going to do an example now, because that's all this lesson really is. We've already met all the kinematic equations. We've already met frames of reference. So what we have to do today is essentially just work through an example and see how all this information we already have applies to a projectile. So what we're going to do is jump over to my document camera, and I'll work through this the same way I would on a whiteboard. The example is a kid throwing a baseball with an initial velocity of 42 meters per second at an angle of 20 degrees to the horizontal. Another kid hits the ball when it is at the same height as it was released. We want to determine how far away the ball has traveled when it is hit. So how far is kid 2 from kid 1? So we'll jump over to the document camera, and we'll just think about it. The first thing that you often want to do with any physics scenario is draw a little sketch of what's going on. I don't really care about the two kids. All we care about is the ball itself. The kids are part of our scenario, but they're not part of the system. The system is just the ball. What's the ball doing? The ball starts here, it goes up, and we've just said everything travels in a parabola, so it's going to travel in a parabola and it'll get hit here. And we know that this is level, right? So it comes back to here. Now, I'm going to choose my frame of reference. As I've already said, for projectiles, we've got y vertical, and that's the positive direction, which means that's the negative y direction, but we don't care about the negative y displacements because the ball's going to stop when it gets back to this height here. And this is our x dimension, and I'm just going to call it positive in the way that the ball's going. That's the simplest choice, is whichever way the ball is going in your horizontal direction, or whatever the projectile is, whichever way it's going, call that your positive direction. It makes everything nice and simple. So that's our frame of reference, and that's what's going to happen, is that the ball is going to travel in a parabola and it's going to stop when it gets back to its original height. And if it's stopping when it gets back to its original height, what that means is that if we call the initial y displacement 0 meters, then the final y displacement is also 0 meters, right, according to our frame of reference. We know that the initial horizontal displacement is 0 meters because that's what we're choosing as our origin. Right, that's our origin. What we don't know is the final displacement. So that's what we're looking for. We're looking for that final displacement. The other things we know, we also know that the acceleration is 9.8 meters per second downwards. Right? And so downwards is in the negative y direction, so negative 9.8 meters per second. And we also know that the initial velocity is 42 meters per second, but it's at an angle of 20 degrees to the horizontal, to the x-axis. So that's everything we know, and it's now written in terms of our frame of reference. what we want to do, first thing we want to do, hopefully you realize, is to decompose this velocity. Because as we said, we can treat it as two separate motions. We can think about the path of the ball going up and then back down. I just realized the sun is making that quite a bad video. There we go. Let's see if that's, no, not quite. The sun is now gone. Right, we have the vertical motion of the ball. It will go up and then it'll go back down. So that's what's going to happen vertically. It's going to start going up. It'll slow down as it reaches the peak, and then it'll go accelerate back downwards. The horizontal motion is just going to travel at a constant velocity all the way across. So we've got to now figure out those velocities. We want Vy and Vx. And as I said already, those are actually just standard formulas. They're the same all the time. We have the x coordinate, x component, I should say, of velocity being given by 42 cosine theta, and the y component being given by 42 sine theta. So again, this is just SOHCAHTOA, the basic trigonometry. If we've got v in that direction and you've got these, that's 20 degrees, then you've got v in the y direction and v in the x direction. Vx is adjacent, so that's cosine, and Vy is opposite, so that's going to be sine. So those are our two equations, and obviously they're pretty straightforward to solve. So we get Vy as 14.36 meters per second, and we get Vx as 39.47 meters per second. As I've said several times, it's a good idea to do little sanity checks along the way. One of them that's very easy to do is just to look at this and say, well, if that's only 20 degrees, we'd expect Vx to be bigger than Vy, and we've got Vx bigger than Vy. But of course, we can check a little bit more thoroughly by using Pythagoras to make sure that if we square these two, add them together and take the square root, we get back to our original 42 meters per second. And indeed, if you do that with those numbers, you will. So now we've got everything in our, we've got our frame of reference defined. We've got all our values given in terms of that frame of reference. We've decomposed everything into x's and y's and so on. Now what we've got to do is figure out how long it takes. What's the time taken for the ball to travel that far? The reason we want to know the time taken is because we know, I will just move the paper down a bit, we know that the change in x is going to be given by Vx delta t. We already know Vx, right? We know that, great, but we don't know this yet. So what we've got to do is use the vertical component to figure out delta t. So we can use the acceleration in the y direction to find delta t. So how do we do that? There's a few different approaches, but what we're going to do is we're just going to write our equation, our kinematic equation for the vertical direction in terms of everything we know. So we know that y final is equal, this is just the kinematic equation, y final equals y initial plus the initial velocity in the y direction. You'll notice double subscripts creep in. When you're working with two dimensions, you want to keep the subscript for x and y, but you also want to keep a subscript for initial and final. So you end up with these little double subscripts. So Vy, so V in the y direction initially, and then we've got that times t minus, what it is, plus a half at squared. I won't put a in just yet. Plus a half at squared. Now we're going to put in the values that we know. So we know that y final is 0. We said that it's finishing when it gets back to 0, and it starts at 0. So we have 0 equals 0 plus the initial y velocity, which we calculated was equal to 14.36 down there, 14.36. So 14.36 times t plus a half times negative 9.8 t squared. Now we can just do math. This is just solving the math problem. So we have, we've got zeros, which you can ignore. This is a negative number, 9.8. So we're going to get negative 4.9 times t squared, but I'm going to move that. Actually, I'll leave 0 on one side. So we've got 14.36t minus 4.9t squared is equal to 0. And for those of you that have done simple math factorizations, this should be pretty straightforward. If you haven't, then in the problem sheets and the solutions, you will see a problem where I do it in 2 steps rather than 1, because the other way to approach this, actually I'll do that after this. I'll do that after I've done this approach, just to show you how it can work. So we factor out the t, 14.36 minus 4.9t is equal to 0. And we can see that this is going to be true either when t equals 0 or when this thing is equal to 0, when 14.36 minus 4.9t is equal to 0. So either one of those is true. When t is 0, that was our start position. So that's fine. We expected that. That's 0 then, because that's how we defined our frame of reference. The other one is the one that must be the time that the ball reaches the second kid. So now we have 4.9t is equal to 14.36. T is equal to 14.36 over 4.9. And that, if you have your calculator, you can double check, but it should come out to 2.931 seconds. So that means that the time that the ball is in the air, the time for it to go up to its maximum height, back down to where it started, is 2.931 seconds. And that is our delta t. Right? That's our delta t. I've switched between t and delta t, but it's the same thing in this problem. So that's our delta t. And we already said that our horizontal position was just going to be given by velocity in the horizontal direction times that delta t. We now know both the horizontal velocity. Remember, that's not changing, so we don't need to worry about saying initial or not. But technically, I should have said initial here, and I should have said initial here. So that's not changing. We've got 39.47 constantly. So delta x is equal to 39.47 times 2.931, which you will find gives us a total distance of 115.69 meters. The values in the original problem were given to, I think, only 2 SF, 2 significant figures. We were given 42 meters per second and 20 degrees. So we would write that as 120 meters to 2 SF, which I've just drawn off the bottom of the page there, 120 meters to 2 SF. So that's the first approach, as I said. I will briefly mention how to do the second approach, but I'm not going to do the math because, as I've said, this is a physics course. So I'll just explain the other approach you could take to think about it. And that is to break the motion up into 2 different halves. Right? Projectile motion is always going to have this point at the top, this peak. And at this peak, the velocity is purely horizontal. There's no vertical velocity. So Vy is equal to 0 at the peak. And what that means is that if you know the initial vertical velocity and you know the acceleration in the vertical direction, then that can give you the time to the peak. That can tell you how long it takes to go from here up to here. And as we're going to discuss, projectile motion is always symmetrical. So that means that if you know how long it took to go from here to here, you know delta t for that part of the motion, then it's going to be the same, we'll call that delta t peak, then that's going to be the same delta t peak to there. And so your total delta t is equal to 2 times that delta t to the peak. And of course, finding out how long it takes for the velocity to change from whatever your initial velocity is to 0 is quite simple, because that was our first kinematic equation. The initial velocity is equal, final velocity is equal to the initial velocity plus AT. Right? And in this case, we're setting our final velocity, which is actually the midpoint velocity, the peak velocity. We're setting that to 0. We had the 14.36 as our initial velocity in the y direction, and acceleration due to gravity is minus 9.8t. And so you could use that to figure out your delta t peak as well, and then double it to get your total delta t, and then solve that, use that to find the horizontal displacement. And so that's actually the same process as what I did here. Mathematically speaking, they both find the same total time of 2.931. So that is the example that I wanted to work through. We'll jump back to the slideshow now. We've got the working is all shown in this slideshow as well. So for those of you that haven't watched the video, or if you want to just reread written slightly differently, then it's all in there as well. As you can see, we get the same answer of 116, although I haven't rounded it to 2SF there, which I probably should have. As we've said, projectiles are always parabolic. They always follow a parabolic path, but where they start can vary. For example, something falling off a cliff. We've talked about dropping something off a cliff, but what if it's going horizontally as it leaves the cliff? So if you throw a ball or a rock perfectly horizontally off the top of a cliff, then it will still follow the shape of a parabola, but it's only going to be half of a parabola because it's starting at that peak. It never gets higher than it is when you let it go. So it's starting at the peak of the parabola, and then it falls down, and that just looks exactly like what we saw to start with the idea of projectile motion. Horizontal displacement is the same every time. You can see we've got evenly spaced dots horizontally, but vertically they're getting more spaced out as the object accelerates downwards. Of course, there can be projectiles that start at different places. So they might start and finish at the same level as we saw with our baseball example. They might start at the top and just fall downwards while moving horizontally as per this image. Or they may start at a different position. They may, if you stand at the edge of a cliff and throw something downwards and sideways, so you might start here, and then it's still parabolic, but you're never reaching that peak. You're starting on the downwards branch of that parabola. Or if you throw it upwards, actually, I might just jump back to the document camera for a moment, just so I can hopefully illustrate this. If you're standing on the cliff and you throw a rock, if you throw it downwards like that, then it will still look like a parabola, but just part of it. You never see the peak of the parabola. Or if you throw it upwards, then you'll get something like that, and it'll still be a parabola, but it's not evenly spaced. You're not starting at the peak and you're not starting at the end. Right? So there's any possible part of a parabola can be your projectile path. If something is just starting with no vertical velocity, so just that half parabola situation, this is another one that's pretty common, as we said, dropping rocks off cliffs or driving a car off a cliff. Hopefully not that common, but they're common examples that we discuss in physics. Then it's just going to fall according to y is equal to half at squared. If we're setting positive y as our vertical, I'm just getting the words in my head the right way around. Positive y is our vertical upwards. That means acceleration is negative 9.8, and so half a is negative 4.9. That means that our vertical position at any point in time is going to be negative 4.9 times t squared. And that means that after 1 second, it will fall approximately 5 meters. After 2 seconds, approximately 20 meters. After 3 seconds, approximately 45 meters, and so on. So you don't need to remember this because you can always calculate it using that basic kinematic equation. But the idea here is that you can see it's accelerating every second, it's falling further and further. So in the first second, it only fell 5 meters, but between seconds 1 and 2, it falls another 15. Between seconds 2 and 3, it falls another 25. So it's getting more every time. This is just like the baseball example. A launched projectile is going to start at the bottom, go all the way up, and then all the way back down. As I said, they are symmetrical, so you can figure out the solution a number of different ways. One way that the textbook suggests for figuring out the solution, or rather thinking about the way we get the solution, is to think about what the projectile would do if there was no acceleration due to gravity. In that case, it would just keep traveling in the direction of that initial velocity. It would keep traveling straight in that line, and you can see that represented here with that dotted vector pointing upwards, the initial direction of motion. And you figure out where it would be after 1 second, or after however many seconds you want, however, whatever time interval you're talking about, figure out where it would be at that point in time if it was just the initial direction and no acceleration. And then you add to that a vector responsible for the acceleration, right, which is, as we just saw, half at squared. And you add that vector on, that gives you where you actually are. And of course, that's exactly what the kinematic equation is. Right? This is what the kinematic equation is doing. You start with the initial position, you add on VIT or VT, and then you add on a half at squared. And if a is in the opposite direction, that'll be a vector that's pointing downwards. So it is literally what the kinematic equation does. It's just a way to visualize it if you find that useful. You don't need to remember this. You don't need to understand the slide if it doesn't make sense, but some people do find it just sort of cements that knowledge a little bit. Once you know the components of the object at any point in time, because remember our kinematic equations don't just tell us the velocity at the start and the end points or the peak, they can tell us the velocity at any point in time, because we know the acceleration, we know the initial conditions, or we know some condition, then we can figure out the velocity at any point in time. And therefore, if you know the two components, you know the total velocity, and we can just use Pythagoras to figure out the magnitude of that velocity vector. Of course, if you want the angle, you'd have to get into the basic trig with the SOHCAHTOA, but there's nothing stopping you doing that. So at any point along that projectile path, you can easily figure out the total velocity. One thing that does save us some work sometimes is understanding what the angle of launch does to the total displacement of a projectile that is launched and lands back at the same altitude, same height. So if you launch something from ground level and then you wait for it to hit ground further away and measure that distance between them, then what you'll find is that if you shoot it at 45 degrees to the horizontal, it will have the biggest possible displacement. And for every degree that you get smaller, you're reducing, every degree that you get away from 45, either bigger or smaller, you are reducing that total displacement. And the thing is that it doesn't matter if you get smaller or bigger by 1 degree, you reduce the displacement by the same amount. So therefore, if you reduce by 15 degrees, go to 30-degree launch angle, or you increase it by 15 and go to a 60-degree launch angle, then they will end up being the same total displacement. That 60-degree and that 30-degree launch angle will give you the same total displacement. This is all for something being launched with the exact same magnitude of initial velocity. So the same initial speed, and you're just changing the direction. So what that means is that any two launch angles that add up to 90 degrees are going to have the same total displacement at the end of their projectile path. And you can see that on this diagram here, we've got 45 going the furthest, we've got 30 and 60 going less but the same as each other, and 75 and 15 going even less but again the same as each other. And hopefully that makes perfect sense if you stop and think about it a moment, because the higher you make the launch angle, if you go all the way up to 75, you've got a lot of vertical launch, initial launch velocity, but not much horizontal launch velocity. So even though it's in the air for a long time, because it has been shot up with a great initial vertical velocity component, it's not moving very quickly sideways as it does that. So it doesn't actually get very far. Meanwhile, in the 15-degree launch angle, it's the exact opposite scenario. You're giving it a big initial horizontal velocity, so while it's in the air, it's moving very quickly, but the small vertical velocity means that it doesn't get to stay in the air very long and it hits the ground very quickly. So the 15-degree launch angle would hit the ground a lot sooner than the 75-degree launch angle would, but they would, in the absence of air resistance and anything else influencing the results, they would land in the same position. Now this is just what I've already been touching on, the idea of the symmetry, the symmetrical motion. The time taken for a projectile to reach its peak and then to travel back to its initial altitude is the exact same time. It is symmetrical. And furthermore, the velocity that the projectile is launched with in the vertical direction will be equal and opposite to its launch velocity at that point. So I'm going to go back to our baseball motion for a moment, just to hopefully make you understand what this is talking about with this vertical velocity. So let's go back to our baseball. We had our initial velocity as being 14.36 in the y direction. 14.36 in the y direction. So that means at the start here we had 14.36 upwards. And what that means is that at the end, it's going to be 14.36 downwards. That vertical velocity just changes by sign. So I should put a negative in there, negative 14.36 according to our frame of reference. And hopefully this makes perfect sense if you think about what acceleration is. Acceleration tells you that every second, the velocity changes by some fixed amount. And so if we've got some fixed time, delta t to the peak, to change 14.36 up to 0, that means the velocity is dropped by 14.36 meters per second in that delta TP. And then this is another delta TP. And because acceleration hasn't changed, then the velocity is going to drop by that same amount again. So it's going to end up at negative 14.36. So that's just exactly a result of symmetrical motion and constant acceleration. So hopefully nothing too surprising there. But again, it can greatly simplify some of our problems. So if we asked you what the final velocity was of this ball, you wouldn't need to do any of that working, because you would know that symmetrically the velocity is going to be the same as what it started, but it'll be pointed downwards instead of upwards. So it can save a lot of time. Again, with questions like range, you can, with range, you don't need to do all the calculations. If all you care about is which goes furthest, just figure out which one's closest to 45 degrees. That's only true if they're launched from the same position, landing back on the ground and being shot with the same initial speed. Graphs, we talked about graphs a lot in the previous lessons. We've covered a fair bit of material, so I won't spend too long on this. But there is one thing I want to point out, is that this graph is y versus x. It's not versus time. So it's just y versus x, and that's just literally a graph of what the motion looks like. If you've got your y position in meters and your x position in meters, you'll notice the scales are very different. The y position is actually starting at 120 something meters, probably 125 based on the scale, and it's ending at 0 meters in the vertical direction. But the x direction is only going from 0 to 5, so it's not actually traveling very far horizontally. Of course, you can, as we've talked about with graphing things for kinematic situations, you can plot each dimension against time. The x position has a constant velocity, therefore it's a straight line. This example here has a straight line with a slope of 1, so it's got a horizontal velocity of 1 meter per second. The vertical motion will look very similar to the graph of y position versus x position, because x position is changing linearly with time. For every 1 second, we had 1 meter. If it was different, if it was every 1 second was 2 meters, then that x position would have just still looked exactly the same, but it would have gone to 10 instead of 5. So it would always look very similar, because that x velocity is not changing. Now, I just want to add in here another comment about frames of reference. You are all hopefully getting to grips with frames of reference. You're starting to look at scenarios and just intuitively start thinking about what the frame of reference is, which is one of the key factors to solving physics problems, especially as we start to get more complicated in the next section with forces. But we have not really addressed the idea of frames of reference in terms of moving between different frames of reference for the same system. So I made a mention in the lesson where I introduced frames of reference about dropping a ball on a train. If a boy's on a train and he drops a ball, or a child drops a ball, the ball seems to fall straight down for someone on the train, but someone outside the train will see the ball moving horizontally as it drops straight downwards. So I just want to go back to that for a moment. So here's a little animation I made of a boy or a child dropping a ball on a train carriage. Our frame of reference that we're looking at is attached to the train carriage. So our y position is the height in the train carriage, the x position is the position within the train carriage, and you can see the x position does not change because our frame of reference is moving with the train carriage. So the x position of the ball never moves because relative to the train, it hasn't moved horizontally. It's moved vertically, obviously. In the Earth frame of reference, though, in the Earth frame of reference, I've made this animation. It's not quite as smooth as I'd like, but I've added the second loop through. You'll see that the line forms showing you the path of the ball, and that is our parabola that we have been talking about, right? So we get a parabola because now that we're stuck on the Earth frame of reference, the ball has a horizontal velocity as well as the vertical velocity when it is released. Vertical acceleration, I should say, when it's released. So in the Earth frame of reference, we get that parabolic motion that's typical of projectiles. In the train frame, just going back a second, in the train frame, it just goes straight up and straight down, I should say. So that's not what we would typically call projectile motion. But because on the Earth's frame of reference, it looks like a projectile, we could still treat it as projectile motion. So there's no real distinction between stuff that is moving horizontally and isn't, because you can just choose your frame of reference to make it moving horizontally or not. So that's just something to think about with frames of reference, and either of them will work. Either of them will work. The laws of physics will work in either frame of reference, as long as the frame is not accelerating. So we've talked about the idea of constant velocity versus changing velocity and acceleration. If your frame itself is accelerating, then the laws of physics start to break. They don't work. So as long as your frame of reference is at a constant velocity and not accelerating, then the laws of physics will work, and you can choose any frame of reference you want. And that is the relativity principle. It's given this name because it is important that just to know that you can use any frame of reference. So the laws of physics have the same form in all non-accelerating frames of reference. That means it doesn't matter if you choose the Earth frame or the train frame, the laws, the equations, everything that we are considering, everything we've talked about will be exactly the same. The velocities will be different, the actual values you put into your equations will be different, but all the equations and all the ideas and concepts are exactly the same. Just the numerical values you get out will be different. And to finish off this lesson, as I promised, we're going to talk about high-speed projectiles and orbiting satellites. So let's think about a bullet traveling very fast. A bullet travels at around about 4,500 kilometers an hour. If you're looking at the very high end, it is realistic for a rifle to travel at that sort of speed though. So if we're looking at 4,500 kilometers an hour, first thing we do, convert to SI units, 12,500 meters per second. 12,500 meters per second is what that bullet is traveling. If the bullet is shot perfectly horizontally at 1.5 meters above the ground, then it would take 0.55 seconds to fall those 1.5 meters. That's just our standard vertical acceleration due to gravity, because of course the horizontal velocity doesn't affect the acceleration due to gravity. That vertical motion is not affected by the horizontal motion. So it will take 0.55 seconds to fall 1.5 meters, and in that time it will travel 6,900 meters or 6.9 kilometers. The problem is, though, that the Earth is not actually flat. So if you shoot something for 6.9 kilometers, then the Earth is actually curved away from the bullet. So the assumptions that we've made, first one was no air resistance. That's something we've treated as consistent for all our projectile motion problems. And at these sorts of speeds, that's a terrible assumption. You cannot assume there is no air resistance for the bullet, but we're going to ignore it for now just for argument's sake, so we can discuss what happens as we get to these sorts of speeds. So as I said, the other bad assumption is that the Earth is not actually flat. In 6.9 kilometers, the Earth's surface will have curved away by about 3.7 meters. So with no air resistance, that bullet has fallen 1.5 meters, but the Earth has dropped away by 3.7 meters. So the bullet would now be higher above the Earth than it was when it was initially shot. So even though it was shot horizontally, it's ended up further away from the ground than it started because it's falling slower than the Earth is curving away from it. In fact, the Earth's surface drops around 5 meters for every 8 kilometers. So if you were traveling at 8,000 meters per second, you'll notice that's slower than our bullet. Our bullet was 12,500. So if you're traveling at just 8,000 meters per second, then every 1 second, you would travel 8 kilometers. But we also saw that in 1 second, you fall about 5 meters. So every second, you would travel 8 kilometers, fall about 5 meters, and then all of a sudden, you're still the same height above the ground. Right? So you'd be falling towards the Earth at the same rate as the Earth is moving away from you. So you would never actually reach the ground if you could travel at 8,000 meters a second consistently. So anything that can do that consistently will never reach the ground. It's unrealistic to do that within Earth's atmosphere. Air resistance is very significant as soon as you get to speeds even a fraction of that amount. So it's not actually realistic or possible to do that within Earth's atmosphere. But if you get high enough that Earth's atmosphere gets very thin or essentially non-existent, then there's no air resistance to worry about, and you can get to those sorts of speeds and you can just fall forever. So you are just constantly moving sideways fast enough that even though you're being pulled towards the Earth, you're accelerating towards the Earth is curving away just as quick as you're moving towards it. And that's exactly what the International Space Station is doing. So the International Space Station, as we saw earlier in the lecture, still has an acceleration due to gravity, Right? It's not quite as high as it is on Earth's surface. It was something like 8.6 instead of 9.8, but it is still there. The International Space Station and everyone and everything on it is still accelerating towards Earth at a constant rate, but they are moving sideways quickly enough that the Earth curves away from them just as quickly as they fall towards it. So the people on ISS, on the space station, or indeed any satellite or thing that's orbiting a planet or a moon, is just constantly falling. That's all they're doing, just falling forever. And so all satellites, all moons, everything, just high-speed projectiles, but they're complicated by the fact that gravity is obviously pulling it towards Earth, and Earth is no longer a big flat surface like we assumed during our simpler projectile motion cases. So that's what I wanted to say about high-speed projectiles and orbits, but I just want to add in one more little note that might be confusing some of you with high-speed orbits and high-speed projectiles. That is the idea that the frame of reference we chose starts to fall apart as well. Right? The frame of reference was that vertical was y and horizontal was x, but what we'll see, I'm just going to draw a little diagram for this. If we have Earth, this is Earth, and we had horizontal and vertical. And our high-speed projectile, we said, well, it's going to be moving fast enough that it stays the same height above Earth. But by the time you get over here, right, the velocity initially was horizontal. Clearly here, it's no longer just in the x direction. But we're saying that it's still just moving horizontally. It's still moving sideways all the time. But that's because our frame of reference has changed. Because vertical, remember, is defined by gravity. It's always in towards the Earth's surface. Gravity always goes in towards the Earth's surface. So that means our frame of reference has changed to being y that way and x that way. So that's why the frames of reference start to break down. So we're not going to deal with that in any great detail. I'm not going to tell you the maths or how to solve any of those problems. I just wanted to point that out in case some of you were wondering how that works. For satellites, depending on how far away from the Earth they are, they have to move at different speeds because we've got the different gravities. And as you get further away, the acceleration due to gravity is less. So satellites that are in close to Earth, so around about 200 to 2,000 kilometers away from the Earth's surface, they're going to need a speed around about 30,000 kilometers an hour, which is 8 kilometers a second, which is the one we we're just talking about. These are the close Earth orbits. And they go around the Earth about once every 90 minutes, so about in every hour and a half. Medium orbit satellites, they're further away, up to 20,000 kilometers from Earth, and they orbit the Earth about twice a day. So they're moving a lot slower than those close Earth orbits, but still moving faster than the Earth is spinning. Geostationary orbits, around about 36,000 kilometers away from Earth, they orbit the Earth once a day, but the Earth is also rotating once a day. So what they do is they actually sync up with a specific location on Earth. And as the Earth rotates, the satellite rotates with it. And so it actually stays above the same point on Earth the whole time it's rotating around the Earth. And that's why we call them geostationary orbits. So you may have heard the term geostationary, and that just means it's far enough away that the time it takes to go around the Earth once is the same as the time it takes for the Earth to turn around once. And that's the end of this lesson. We're not going to deal much with satellites and high-speed projectiles in that sense. I want you to be aware of them. If you ever get questions about them from this course, it would be very generic questions about the concepts of them. We wouldn't ever do any of the actual maths or equations relating to them. But we will deal with projectiles a lot. You do need to be very comfortable with the projectile motion, which, as I've said, is no new physics. Just taking everything we've talked about for frames of reference for constant acceleration motion and constant velocity motion, putting them all together and solving these two-dimensional projectile problems. Now, you do need to be able to do that, not just for kinematic questions, but because as we move through into more physics, as I keep saying, a lot of physics is intertwined. When we start talking about different forces and different effects on different objects, we will see that projectiles are common not just in these special cases that we've made up, but actually through a lot of areas of science.